So my topic this morning will be quite related to the purpose topic that was previously mentioned in the previous two talks. But as you will see, I will adopt a slightly different perspective on how to make useful robots just through social interaction with these robots. And I will build this talk about the notion of inferential social learning that I borrow from Yo Gueon, and okay, I will go into that. So a quick overview. I will start from the open-ended learning challenge, as a lot of people here. I will show you that the kind of agents that we tend to build are missing some social capabilities that are precisely inferential social learning capabilities. Then I will propose a formal framework to account for inferential social learning, and then I will show you a few of our contributions in that domain, so as to exemplify what we can do to improve our agents with these inferential social learning capabilities. And finally, some word about the benefits that we can draw from the large language model achievements on that topic. So to define open-ended learning agent, I will just use exactly what Jeff Clune said yesterday. He said an open-ended learning agent is a learning agent that learns new things forever. I think that's the simplest definition we can give, that tells just what the word is about, open-ended learning. Okay. And if our agents are autotelic, that is, if they invent their own goals and tasks, okay, it means that they have to invent their own goals and tasks forever. And that's very challenging. If you think of it, even ourselves, we are stuck in a room for 3 days. After some time, we stop inventing new goals. We just don't know what to do. Okay, so we need some external solicitation or some strong mind to keep inventing new goals and keep busy with doing things if we are not solicited by our environment. Okay, so that's not easy to design agents that will learn new things forever. That's the general point. And in that respect, I think agents that can have social interactions with other agents will help a lot. Okay, so here we have a drawing where we have here an autotelic agent, that is, the agent as an internal goal sampler. Okay, it will sample its own goals, and it will learn to achieve these goals through reinforcement learning or whatever. But we don't want these agents to be only autotelic. We would like also them to be teachable. It means that an external social partner can suggest different goals to the agent. Okay, and the fact that the agent can be influenced by other agents makes the open-ended learning challenge much easier, because the the social partner may suggest new goal spaces just by asking the agents to do things, by telling that it could do things. Okay, it could suggest many more goals than the goals that the agent could discover by itself. Okay, that's why one of the reasons to be interested in social interaction when we are interested in open-ended learning. Okay, I must say that in the perspective that I am drawing here, social learning just appears as complementing sensory motor learning from an autotelic agent. Okay, but there is a more fundamental Wittgensteinian perspective that social interaction could be a necessary condition for the emergence of complex sensory motor intelligence. And that's the kind of work that is mentioned in Cedric's and Pierre's recent work, for instance, that paper. Okay, but I won't go further in that direction in this talk. I will just adopt the view that social learning may complement sensory motor learning. Okay. Now, what's inferential social learning? So I take this notion from Yo Gueon's paper that is mentioned here, okay? And she says that inferential social learnings aims to characterize the interactions between two agents, the teacher and the learner, okay? And that interaction results from mutual mental state reasoning and planning. Okay? And what does this mean? The first way to show you what it means is to take a few examples. That's what she does in the paper. So for instance, okay, you will have a teacher agent and a learner agent, and the teacher will show things to the learner. For instance, if there is a box with two kinds of toys and the blue toys are squeaking and the yellow toys don't, if the teacher only draws the blue toys and shows squeak, the learner, a human learner, will infer that the yellow toys don't squeak, okay? Which was not shown, so you need to infer that, okay? And why will the learner infer that? This is just because the learner generally assumes that the teacher is maximally informative. So if the yellow ones were squeaking too, probably the teacher would have taken a yellow toy and show that it squeaks. Okay. Same thing if you have a toy with, and the teacher only shows one property of this toy, the learner will infer that this toy has only one property. But no, if the learner knows that a toy has several properties and the teacher just shows one, the learner may infer that the teacher is under-informative. But there is an even more complex situation. If the learner knows that the teacher knows that she knows that the toy has several functions and the teacher only shows one function, the learner won't infer that the teacher is under-informative. It will infer that he's not showing the other functions, but because the learner already knows these functions. Okay, so you can infer about a model of the other one to determine what's the exact situation. Okay, that's a very powerful mechanism which allows you to draw much more information from what the other is showing or not, depending on what you know about this other, and you know that this other knows about you, etc., etc. Okay, so that's much more powerful than what our reinforcement learning agents do when they interact with each other. Okay, that's the general idea. I hope you got the example, even if it's a little involved. Okay. Okay, and then with colleagues, most of them are in the room at the moment, we wrote a kind of survey paper where we took a list of expected properties from learning agents based on the developmental psychology literature, okay? And then we surveyed different classes of agents and a few of our own agents. And it was quite obvious from this survey that if you take the OR between the properties of those different agents, the properties that are not covered mostly correspond to inferential social learning capabilities. So it means that the main class of mechanisms that is missing in this literature is related to these inferential social learning capabilities. Okay, so that's the point of my talk, that I will try now to show you that we started after discovering this to try to put inferential social learning capabilities into our agents. So before showing you a few examples, I will try first to set a formal framework. Okay, in fact, I will borrow this framework from Mark O, but before using it, I will just give a short reminder about Bayesian inference. It will be a lot based on Bayesian inference. So just so that you get the idea, in Bayesian inference, you assume that you have some hypothesis, and based on this hypothesis, causality will generate some data. And in inference, you are observing the data, and you want to infer what are the corresponding hypotheses. Okay, and the Bayes rule tells you how to infer the hypothesis from the data if you know the probability of the data, the probability of the hypothesis, and the probability of the data given the hypothesis. Okay, so that's the causal way, that's the inference way, and inference can also be called inverse planning because you are using this graphical model in the reverse way with respect to causality. Okay, that's the very basics, let's say. Yeah, and this idea that inference is inverse planning is presented in that particular paper. Now, how can we apply this Bayesian inference tool to the inferential social learning framework? I will have two agents. One will be a demonstrator and one will be an observer. Okay, and I need several elements to define them. Okay, all these. Okay, so the demonstrator might be acting in an environment, and it may try to achieve some goal in the environment. For instance, get the key. Okay, that would be the instrumental goal. The demonstrator may have some beliefs about this environment if not everything is observed. Okay, but the demonstrator may also have some belief-directed goals, which means that he would like the observer to believe something about the environment. Okay, by giving a demonstration, he may change the belief of the observer by showing things about the environment. Okay, he may also have some model of the observer, and based on all these elements, his policy will tell the demonstrator which demonstration it should do. Okay, that's the general idea. From the side of the observer, it also has a policy. It observes the demonstration. It has some model of the demonstrator. And from those two elements and its policy, using inference, which is inverse planning, it might infer what's the instrumental goal of the teacher, what was it willing to show, and eventually what belief, how it should update its belief. Okay, so Bayesian inference will allow you to make these things. So, okay, and in the particular case of a pedagogical demonstrator, it will act to influence the beliefs and goals of the observer based on the model of that observer. Okay, and the pragmatic observer will infer the instrumental and belief-directed goals of the demonstrator based on the model of this demonstrator. Okay, I will make the difference between this case of pedagogical and pragmatic with respect to more naive agents later on. Okay, this setup is close to the one proposed in that particular paper. I just added this idea of belief and changed a few small definitions. Okay, what is nice with this model is that we can use it recursively, because if you see here the observer as a model of the demonstrator, but as model of the demonstrator, we can take this model. Okay, that's so here as a model of the demonstrator, I'm plugging the model of the demonstrator itself. But in the model of the demonstrator, there is a model of the observer, and in the model of the observer, there is a model of the demonstrator, etc. Okay, so using these graphical models, you can account for the fact that the observer thinks that the demonstrator thinks that the observer thinks that the demonstrator thinks, etc., ad infinitum. Okay. So it means that if you want to use such a recursive framework, either you need some approximate reasoning framework, or you need to have an early stopping criterion. Okay, and Mark O again suggests that people tend to have an early stopping criterion, so they won't infer based on thoughts of the other about thoughts about the thoughts, etc., etc. They will stop after 2 or 3 levels maximum. Okay. And the third element that we need to formalize these things is a notion of utility. Because if you observe the behavior of an agent, to understand its goals, you have to have a rationality assumption and to say this agent is trying to maximize that particular utility so that you can infer the goal from the behavior. Okay. And what's interesting is that Mark O suggests to take this utility notion from optimal decision making, so standard reinforcement learning utility. And in the task that Mark O is using, his utility is derived directly from a reward signal. Okay. But what's interesting for us, where we are in an intrinsically motivated workshop, is that in the framework we have goals. So rather than using standard reinforcement learning and reward functions, we can use goal conditional reinforcement learning, and utility will correspond to goal achievement. Okay, that's a slight change with respect to what Mark O is suggesting, and that's an important modeling decision. Now let's show you a few contributions using this framework that we tried to achieve with different people here in the room. So the first work was related to what we call communicative demonstrations. Okay, the idea went by reading this very seminal paper from Jérôme Brunner and his team. Okay, that's a very cited paper, The Role of Tutoring in Problem Solving, where we can find this sentence at some point. In all instances observed with these 30 children, there was not a single instance of what might be called blind matching behavior. Okay. Today, blind matching behavior would be what we call behavioral cloning in machine learning, okay, where you just copy paste the behavior of the demonstrator into the learner, and the learner will do the same thing. Okay. What they say is that this does not happen in social interaction between children and teachers. So to account for that, we took two different types of demonstrator and two different types of observer. We have the pedagogical demonstrator that I've shown you about. We could simplify a few things because everything was observed in our case, so we did not need any word belief, okay? And an important simplification that we made is that instead of inferring what to do based on the model of the observer, the demonstrator was determining what to do based on its own policy. Okay, it didn't have a model of the other. And the same for the observer. He was interpreting what the demonstrator was doing based on its own policy instead of a model of the observer of the demonstrator. Okay, that's simplifications. And with respect to these two kinds of agents, we also have just a naive demonstrator that has the goal, a policy, and that just achieves the goal with the policy using reinforcement learning. Okay, and the literal observer again has no belief about the others. Okay, it just has a demonstration and it will infer the instrumental goal as in behavioral cloning. Okay, and the topic of the experiments is related to goal ambiguity. Someone said this morning that humans are always ambiguous. Okay, they are ambiguous when they are using language, but they are also ambiguous when they demonstrate things in the world. Okay, so our example is a case where the agents have a set of blocks in front of them, and they can achieve different configurations of blocks. Some can be close to each other, some can be on top of each other. Okay, we have three blocks, so we have a set of, I don't remember how many configurations. Anyways, and for instance, if your goal is to have the blue block close to the green, and you are doing the demonstration by taking this blue block and putting here, the learner cannot determine if your goal was to put the blue block close to the green or close to the red. Whereas if you take this green block and you put it close to the blue, your learner might infer that, in fact, they might correctly infer that the goal is to put the blue close to the green. Okay, so this demonstration is less ambiguous than this one. That's the idea. Okay, and to account for that, we use a mechanism which is called Bayesian goal inference. In fact, we have goal condition policies. Okay, and if you have a goal condition policy and you know the goals, it will give you trajectories. By inference is the other way around. So you have the trajectories and you infer the goal. Okay. So to get pedagogical teacher, we have a teacher that will that will adapt its policy so that the goals, so that the trajectory it produces are the less ambiguous possible. Okay. So in more details, because I want this part to be clear, the standard teacher will just select a trajectory without inference, and the pedagogical teacher will try different trajectories, infer the goal that it would have inferred with its model given the trajectory, and select the trajectory that corresponds to the less ambiguous goal. Okay. Conversely, the learner will use Bayesian goal inference to try to infer the goal of the teacher, and then will interpret the demonstration using this goal inference mechanism. Okay. And the idea is that if the learner correctly infer the goal, both the teacher and the learner will get rewarded because the communication was non-ambiguous. Okay. And with this work, I forgot to mention that this is some NeurIPS work. We could show that in the case where there are many demonstrations all combinations of naive, literal, pragmatic, and pedagogical work okay in that case, okay, all agents succeed. But if in the regime where you have only few demonstrations, the literal and naive perform much less well than the pedagogical and pragmatic, because the pedagogical and pragmatic agents communicate much better, so they succeed much more. Okay, that's the first idea. Okay. And now what's interesting is that in the pedagogical and pragmatic pair of agents, we account for what Jérôme Brunner says, that the behavior of the teacher and the behavior of the learner do not match. Okay, they match through the goals, but the teacher is not doing the same movements as the learner. That's the general idea. Okay, and another point is that in Marco's framework, everything is given, whereas here we are using reinforcement learning, so the goal condition policies are learned by the agents through time. So we account for learning in inferential social learning, for the learning part of inferential social learning. Okay, but there are some limitations to this work, and the first limitation is that first we train the teacher to be as pedagogical as possible, and then we use the agent using demonstration from the teacher. Whereas it would be much more interesting if the teacher was trained in front of a particular agent and would adapt its policy to that particular agent. Okay, but for that, we would need the teacher to have a specific model of the learner, and the learner have a specific model of the teacher. Okay, that would be having a theory of mind, and that will be the second part that I will tell you about. Okay, so the idea is that in the work of Clémence Creslin, who is here also, we are now interested in trying to infer beliefs and making a model of the author partner in a quite different setup. Okay, so the setup is again inspired by your work by Yo Gueon and a few co-authors. Okay, this starts with an experiment with two infants. One is showing a toy, how to use a toy to another learner infant. Okay, and the idea is that this toy has 20 buttons, but only 3 of the buttons are displaying music when you press them. Okay, and what's interesting is that if the teacher infant does not know nothing about the learner, it will press all the buttons so that the learner knows which are actually displaying music. But if the teacher could observe before that the infant was playing with the toy before, it will only press the 3 buttons that display music, because it knows that the learner knows that some of the buttons don't make music. Okay, that's the kind of inference that we can get. Okay, and we wanted to reproduce exactly the setup with Clémence's work. Okay, so for that we need to have 2 environments. There is first an environment where the teacher is just observing the behavior of the learner. Okay, and from this observation and some models, the teacher will infer what's the utility of different possible demonstrations, okay, and will play in another environment the demonstration that is suspect will have the greater utility for the learner. Okay, some things that I did not say and which is very important in that particular story is that there has to be a cost of the demonstrations. Okay, otherwise the best strategy is always to display all the buttons. Okay, but if you want to make profit, that you know something about the learner and that you can only display 3 buttons, if you take into account the fact that demonstration is costly, then you can choose a shorter demonstration, leveraging your knowledge of the learner. Okay, and with this experiment, we could account for that particular behavior. And okay, so just to cast this into the formal framework that I've shown you before, what do we have here? If we have a pedagogical teacher, the teacher still does not have any belief about the world, it knows everything, but it has a model of the learner. So it observes the behavior of the learner, and from this observation of the behavior of the learner, it will infer what is the instrumental goal of the learner and what is its work belief. And using this work belief, it can extract some belief-directed goal and some instrumental goal so as to select a demonstration that will be suitable for that particular learner. Okay, And the learner itself in our experiment is fixed. So we are not interested in the part of the literal learner learning. Okay, so we have a fixed policy learner. The only things that change with the learner is that it has a word belief about the environment. In the case of the first experiments, the belief is where are the buttons that display music. So in the beginning, the learner knows nothing, but after being shown by the learner or after interacting with the toy, the learner might update its belief, showing more and more precisely which are the correct buttons. Okay. And then we transposed the same experiment into a more challenging artificial intelligence-oriented framework. So that's the mini-grid environment that was shown before yesterday evening also by Jeff Kuhn, okay, where the agent has to take keys to open doors of the same color and has some limited perception of the environment. So in that particular case, having a belief is important because in the beginning, the learner does not know the position of the keys and the doors, so it has to explore. Okay, and in that particular case, the teacher will select the demonstration that will help the learner determine where is the key and the door that he is looking for as efficiently as possible. And a key difficulty in that particular case is that there are different agents, the different learners, sorry, and these different learners have receptive fields of different size. So it can be 3 by 3, 5 by 5, 7 by 7, etc. Okay, and depending on the size the teacher infers for the learner, it will have to go closer to the key to show it where the key is. So the demonstration will be different depending on the size of the receptive field. Okay, and what Clémence is showing with her work is that by modeling the learner through observing its behavior in a particular case, the teacher will be able to perform the most adequate demonstration for that particular learner. So here is an example where that's the observation. So you can see the trajectory of the learner, and through the trajectory of the learner, you can see what the teacher infers about that particular learner. So in the beginning, it believes that the learner is going for the yellow key, okay? But then it says that that's not the yellow key because it's passing close to it and continuing. So in fact, it infers that this is the purple key. And here, the darker, the smaller it believes the receptive field is. Okay, so if in the beginning it thought that the agent had a big receptive field and was looking for the yellow key, and then it decided no, in fact it's looking for the purple key and going further. Okay, and okay, I can't give you the final results because Clémence just told me this morning that no, she has them. Okay, but the general idea is that the teacher endowed with this model of the learners and these inferential learning capabilities perform better than teachers that don't have a model of the learner, which is quite obvious. Okay. Last topic, how much time do I have?
7 minutes.
7 minutes,
including the Q&A.
Okay, perfect. Okay, so in what I've shown you so far, the interaction between the teacher and the learner was only through demonstrations. Okay, but what I said with this framework is also correct with language. Okay, this is said explicitly in the Shafto and in that paper, okay, from Goodman and Frank, that's not Shafto. What you can say about pragmatic and pedagogical demonstration is also true of pragmatic and pedagogical language. Okay, you can be more or less explicit in language and select what you will say in a more or less ambiguous way. Okay, so with Hugo, who is there also, we decided to reproduce these demonstration experiments also by interacting with language, and then we got interested in second question, which is also in Brunner's papers, which is in which situation shall we more use a demonstration, and in which situation shall we more use language? Okay, and in fact, in Jerome Brunner's paper, they say that with younger children, you use more demonstrations, and with older children, you use more language. Okay, and we decided to try to reproduce this. So basically, this is Hugo's poster. So I suggest you to have a look at Hugo's poster if you want to know more. But the general idea is that here you have the learning efficiency measures as the area of the curve of the different pairs of learner teachers. Okay, and you can see that demonstration only, instruction only is the least efficient, and that demonstration then instructions is more efficient than having instruction then demonstrations. So if the knowledge of the agent is growing, it's better to first start with demonstration and then go for language. There are other related works on the same topic, but a completely different perspective that I will mention very briefly. Okay. The idea is that, okay, this comes from Thomas Eleo's work, that children understand knowledge acquired through instruction as objective truth and generalize language much better than acquired knowledge acquired by other means. Okay, so if you give a demonstration, okay, I go fast. Okay, so the general idea is that language helps generalizing better. And there is also this paper where they show that the key thing is that the demonstration just shows you a unique instance. So from a few instances, you have to infer the rules, whereas with language, we give you directly the rules. So when what you want to learn is complex, it's easier with language because you can convey complex rules with language more easily than complex demonstrations. Okay, a quick word about future work. There is this paper, again, Mark O and Rebecca Sachs and a co-author that I know less, planning with a theory of mind, where they show that, in fact, we don't use theory of mind in all situations, but more when we are facing a novel situation in our social interactions. Okay, otherwise, we rely on habits. But we tend to infer what's the goal of the other and what demonstration or what language we should use when the situation is novel for us. Okay, and they claim that if we want to generalize ways to unseen situations, we need to manipulate abstract representations, and that language is mostly appropriate for that. So they suggest that theory of mind should be mostly language-based. Okay, so it would be interesting to try to design agents where the language, the inference capabilities about the model of each other, etc., is done in a large language models when they are endowed with some inference capabilities. A few limitations to this perspective. The first one is that there are some good evidence of theory of mind in non-verbal animals, in few birds and chimps, etc. And the other point, which I find even more interesting in this paper, is that we need a theory of mind to acquire language, but we also need language to acquire a theory of mind. So there is a very interesting developmental process here, and that we should not just plug an existing large language models and use it to have a theory of mind. We should more be interested in how to develop these things together. And finally, if we have an agent with language-based theory of mind, it could have a theory of mind about its own behavior. And that's very interesting because this agent could explain what it's doing in easy to interpret ways for humans. So it could say things like, I did this because I wanted that and I thought that. So when you justify what you are doing, generally you are using theory of mind-like explanations. Okay, you explain what were your motivations, your desires, your thoughts, your beliefs. Okay, and this could be a key towards interpretable and explainable AI to build some theory of mind on top of our sensory motor learning agents. Conclusive remark. Okay, again, I'm moving to a more recent paper from Yo Gueon, where she investigates what it changed to have these inferential social learning capabilities in machines. And I like a lot these 2 points, that if we want to have teachable machines, so our teachable agents, these machines should behave as human learners. So they should be endowed with inferential social learning capabilities. Okay. And if we want to have teaching machines, they should also behave as human teachers. So they should be endowed with these inferential social learning capabilities. Otherwise, for the human interacting with the machines, part of the story will be missing. It won't be able to infer as we infer when we interact with each other. And that's it for today. Okay, a word about the collaborators. They are all in the room except Ahmed. So you can go and speak with them if you want to go further. Thank you.
I think the non-verbal theory of mind is something that does appear in animals. I mean, anyone who has seen dogs behave in non-verbal, they have definitely a theory of mind, at least the intelligent ones. So I don't think you need language for that.
Yeah, I agree.
What I find very interesting is your observation that there's a case where actually demonstration is more efficient than theory of mind, than language becomes more efficient. In my opinion, that's very deep insight. I don't know. I'm not exactly sure what it suggests, but I feel that it tells us something about not just that language allows you to generalize, but my question is actually, what does it actually tell us about the transition from understanding embodiment, if you like, to understanding, say, kind of abstraction? Do you have any views on that?
Abstraction is one of the key problems to me. Okay, I'm a reinforcement learning researcher, and let's say that having agents able to abstract representations from sensory motor interaction with the environment, to me, is one of the most fundamental problems that we don't know to face at the moment. So no, I don't have. I have thoughts about this, but just speculations.
Thank you for this really wonderful talk. I guess my question is about, so in your talk, you kind of described the social agents as both a really large source of data about goals and beliefs that the learners can benefit from. And I guess I'm curious, there's this other perspective which you can think of learning as maybe self-teaching. So if you can represent agents, you could maybe just imagine a different agent. Imagine different beliefs, imagine different goals, and kind of use that without the actual observation, right? And I don't think necessarily that's what humans do, but maybe in the, for AI, that might fine. I'm curious what you might think of that. And then if you want the multi-agent scenario where cultures sort of this even larger historical knowledge about worthwhile goals and beliefs, then maybe the large language models kind of stand in. I'm just curious what you think about this.
Yeah, I think your remark is very related to Vygotsky's notion of internalization, but the other way around. Okay, the idea is that when a kid is cared about, okay, there are adults saying things to a kid, the kid will tend to repeat for itself what the adults are saying. Okay, and little by little will internalize. Okay, first it will repeat loudly and then repeat in its head, and finally it won't even repeat it in its head. That's just incorporated in its way of behaving. Okay, so is getting things from an adult into itself. But I think you are right. We also tend to speak to ourselves as if we were speaking to someone else, so as to plan, so as to etc. So I don't know if this is exactly what you are pointing at, but yeah, we tend to interact with fake agents. And that's a way to use language, etc., to plan our behavior and to determine how people would react to our behavior, etc. Yeah, so that's very interesting. Yes.
Thank you.